So this video is a short review of how to get an empirical formula as well as a molecular formula. Remember what an empirical formula is. It is the smallest whole number ratio of essentially of moles in the compound. Right. So empirical so basically when you have if you have 1 mole of water, if you have 1 H2O, right? That means for every 1 mole of water, there's 2 moles of hydrogen to every 1 mole of oxygen. That's literally what that means. Now, sometimes the molecular formula is the same as the empirical formula. It depends. The molecular formula tells you the numbers and types of atoms in a molecule. And a molecule, is not necessarily going to be a small whole number ratio. So a single piece of water happens to have a molecular formula and empirical formula the same, because every water molecule, you have 1 of these oxygens with 2 of these little hydrogens, right? But some molecules are different. For example, C2H4 has a structure like this. It's got a carbon with another carbon with 2 hydrogens like this and 2 more hydrogens over here. That's what a single molecule of this substance looks like. That's its molecular formula, but its empirical formula would just be CH2. What you basically did was you divide both these numbers by 2, and that gave us our empirical formula, which is basically a smallest whole number ratio. So let's look at an example problem. Now, molecular formulas and the gram molecular masses of molecular formulas are determined by what we call volumetric analysis or other tools or techniques. Gravimetric analysis allows us to determine the empirical formula. That just means if we find out the proportion of masses in a compound, we can convert that to a proportion of moles, and we can reduce that to the smallest whole number ratio. So, given that you're starting with percentages, for example, let's say you have a substance with a GFM of 283.88, and it's made of 2 elements, just phosphorus and oxygen, and the ratio by percent is 43% phosphorus and 56% oxygen. All right, well, the first step you can do is you can do an assumption. And the assumption you kind of always want to do is you can assume you have 100 grams if they start you with percentages. So you convert that into grams and say, okay, I have 43.64 grams of phosphorus, and I have 56.34 grams of oxygen. And I can convert that into moles very easily. Now remember, in these cases, we're not going to use the formula for oxygen as its diatomic, because this is oxygen within a compound, not oxygen as an element. So we're going to take 16.00 grams as 1 mole and divide through, and that's 1 mole of oxygen. And we're going to get the moles of oxygen. We're going to do the same thing for phosphorus, whose formula mass or average atomic mass is 30.97 grams as 1 mole of phosphorus. And when we do the math here, we get 1.409 moles of phosphorus for every 3.523 mole of oxygen. And so what we did so far is that step 1, we turned the percentage into grams. Step 2, we turned our grams into moles. Step 3, we tend to divide by the smallest number. And the reason why is because that turns one of these numbers into 1, because we're looking for a whole number ratio. Okay, because that's just how we, like it. We like to have a nice whole number ratio for formula. So we're looking for the smallest number, and that in this case is 1.409. So we divide both these guys by 1.409. Okay, and when we do this, we get 1 mole of phosphorus for every 2.5 moles of oxygen. And what we want to recognize at this point is we have a formula like this, P1O2.5. That's not a whole number ratio. And because this is off in the tenths place, we're not going to round this. So we're not going to say this is P103 or P102. If it's not near enough to a whole number that it's off by less than a couple of hundredths, we're not rounding yet. So then the fourth step sometimes is we're going to have to multiply by some number. And we're going to multiply by some number that's going to turn into a nice whole number ratio. And so what we can do, we can multiply both of these guys by 2. And if we do that, we're going to get, right, so that's our last step. We'll get an empirical formula of P2O5, right, because 2 times 2.5 is exactly 5. And you're usually going to multiply by 2 or 3 or 5 or something like that. I've never seen one that's larger than 8 or 9, and definitely not in my class. You won't see that unless, let's say, you're looking at something on the AP exam, perhaps, and even that's a stretch. Now, the fact is, if you add up the P's and the O's here, okay, since you have 2 of these guys, and I'm going to do 2 times 30.97, and you got 5 of these O's at 16.0, you're going to find that the empirical formula does not match the molar mass, because this, when you add this all up, you get 141.94, but the gram molecular mass is 283.88. So this is your empirical formula. We've got the first step here. We know what that is. We don't know if this is the molecular formula. If it turned out that GFM was 141, that would mean that the molecular and the empirical formula were exactly the same. But if it doesn't match, then what we do is we take this number here and we divide it into the bigger number, which is the gram formula mass. We go 283.88. Now when this happens, it's always going to come out, unless obviously it's done in an experimental setting where things might be off, but on a problem you're going to see on a test or an exam, it's always going to work out absolutely perfectly. And in this case, if you divide the three, you get the number 2. And what this means is that the molecular formula, okay, is twice as big as the empirical formula. So this number here is what you're going to multiply the subscripts by. And the subscripts are those little numbers down to the right of the elements. So you're going to multiply the P2, this 2 right here, you're going to multiply that by 2. So you're going to be getting P4, and you're going to multiply this little 5 over here by the 2 as well, and so you're going to get O10. And this right here is going to be your molecular formula. And again, I haven't shown you how to get this molecular mass yet. That's going to come up in a subsequent unit, but I'm probably only going to show you 1 or 2 ways to do it this year, but there's a lot of different methods by which you can determine what the molecular weight is, and therefore determine the molecular formula by combining gravimetric analysis by other forms of analysis.